Uniform pressure theory and uniform wear theory. So for this clutch and cone clutch, usually we have these two theory here. One is uniform pressure and the other one is the uniform wear theory. Now, before that, okay, let us take a look at the terms that we use in this clutch. So we can have this single disc or multi-disc clutch. Okay, so FR, the subscript, the symbol FR with the subscript R, the F with the subscript R here, actually we are referring to the frictional force. W is the spring force or the axial force or normal force, where mu is the coefficient of friction, R would be the mean radius. Now the mean radius for a disc clutch, it depends on whether we are referring to the uniform wear or the uniform pressure theory. And then R1 is the outer radius. So as you can see from the disc, okay, or from the frictional lining or from the disc itself. So this here we have the internal diameter. When you refer to the outwards, that means from this point here that I'm pointing towards this point here, that is the outer radius. So from here to here would be the outer radius, and then from here to here would be the inner radius. And then you have pressure, axial pressure or axial pressure acting on the surface of the friction lining material. Now this red color thin, how to say, rectangular strip here, this part here is actually the friction lining. Okay, your friction lining is here and here. Okay, so this can be the disc plate. Okay, so R1 refers to the outer radius. This is the outer diameter. So half of this would be the outer radius. Okay, so you have R2 for the inner radius. This is the inner radius. So, and B would be the width of the frictional lining material. Width of the frictional lining material. So how to get the width is by taking R1 here, this length here, minus of this length. So you will be able, to find out the width here, this width here. That is the width of the frictional lining material. T would be the torque exerted or the torque transmitted by the clutch. N is the number of pairs of contact surface. The P that we use here is the power transmitted. And the lowercase letter p will be the pressure exerted, the axial pressure or the normal pressure here. This pressure here usually is exerted by the spring. Okay, you have springs placed, okay, in between the clutch and the pressure plate. So N is the speed, the rotational speed in RPM or RPS. Okay. So now, when you refer to this diagram here, okay, and this would be your frictional lining. This would be your frictional lining. So when there is another plate come into contact, with this lining here, what happens is, let's say the pressure plate, okay, presses onto this surface here. What happens is it will exert a force. Okay, this is called the axial force. Okay, or the actual force or the axial force here and here. That means actually is uniformly distributed on this surface here. All this force here, the blue line ones. Okay, so not only 4, you might have a series of these forces here acting on this surface. When there's another plate, okay, presses onto this surface here. When there's another plate here, let's say if there's another plate here, presses onto this, what happens is it will actually exert a force, an axial force onto this surface, and we call this as the normal force or the spring force or the axial force. So when these two surfaces here, earlier I've said another plate or the pressure plate, okay, pressing onto this surface here. If let's say it starts pressing onto this surface, what happens is it will, when the disc starts to rotate, it will actually induce or produce okay, these forces here, these forces is called the tangential force, or most of the time we call this as the frictional force. Because when you have two surfaces in contact, okay, one plate, this is one plate, and here you have your frictional lining, and then when you have another plate on top of it, what happens, and it presses onto the frictional lining, actually you have normal force normally when you refer to friction. So normal force is actually always acting 90 degrees to the contact surface. So when the thing starts rotating, what happens is it will create a rubbing onto this surface. This rubbing force is caused by the pressure plate that is presses onto the frictional lining. Okay, so that you have this force here, that is the spring force or the normal force, and that will create a frictional force or a tangential force here or onto this surface here. So we call this as the frictional force. Okay, so now frictional force is equals to the product of mu Rn or mu R. So mu is the coefficient of friction, R is the normal reaction here, these normal forces here. Okay, I hope you all can get it. So you can see here you have pressure distributed onto this frictional lining. Okay, so or this diagram here, as you can see, okay, if the normal force is acting, or just let's say for example your hand presses onto the surface of this plate, your hand presses onto the surface of this plate, actually your hand is actually exerting a normal force onto this surface, and if this start to rotate, what happens is your hand will start rubbing against this surface here, so and it will produce frictional force as is shown in the red lines here, like that. Okay, so we know that frictional force, define frictional force. Frictional force is defined as coefficient of friction multiplied by, or the product of coefficient of friction with the normal force. And the normal force that we have here is the spring force. This one, they are the normal force. 90 degrees to the contact surface. Your hand, you place your hand, your palm on top of this, and when it rotates, and then when you exert the force from your hand onto this surface, is actually the force that is exerted onto this surface. This is the normal force. So when this plate starts to rotate, it actually produce these forces here, which we call the frictional force. So the normal force the frictional force is actually defined as coefficient of friction with normal force. But in this case, the normal force is the spring force, the spring exerted by the pressure plate, which is between the pressure plate and the disc, or outside the pressure plate. Okay, so the frictional force therefore is equal to the product of coefficient of friction and the axial force here. So, and we know that torque is defined as tangential force multiplied by radius. So the tangential force in this case here, these are the tangential force, is the frictional force multiplied by the radius, that is the mean radius. The mean radius you consider from the center of this point here to the axis of the disc, to the central axis of the disc, then you can consider that as mean radius. So if this frictional force multiplied by this radius will give you a turning about the center here, okay, which is equals to frictional force times radius, that is the torque. So, and we know that frictional force here is equals to the product of coefficient of friction and normal force multiplied by radius. Now this Rn here is not normal force, W here is the normal force or the axial force or the spring force. The R here is the mean radius. The N here is actually the number of pairs of contact surface. The number of pairs of contact surface. Okay, so if we were to refer to a single disc clutch like this, the number of pair of contact surface is actually one side here, one pair here. That means between this, the disc and the pressure plate, and another pair is supposedly to be here, that is between the disc and the flywheel, which is at the back. Okay, so N for a single disc clutch, the N is always refers to 2. That means 2 pair of contact surface. surfaces. Okay, so as you can see, it is acting like this. So you can see the normal force is actually acting on the surface of the frictional lining, and then because of that, okay, it creates tangential force or the frictional force like that. So you see this diagram here. Okay, so the normal force is acting on the surface, and when this rotates, when the disc rotates, it actually causes a rubbing between the surface of the frictional lining and with another plate that might be the pressure plate, which is in contact with the disc. So these forces that is acting or pressing onto the surface of the disc will also at the same time produce frictional force. Okay. So for the analysis of the disc clutch here, okay. So this is your normal force. These are all your normal forces or the spring force that is acting on the surface of the disc. Okay. And then as a result of that, it will create a friction. It's just like, for example, when you refer to the previous slide, this one, this is the general formula for the torque transmission for a disc clutch. That is for a disc clutch. Excuse. Okay, so T is the torque, P is the pressure, R1 and R2 is the external and the internal radius, R is this R here, or you can use the uppercase letter R as for the mean radius, mu as the coefficient of friction. So when you refer to the clutch here, okay, you just assume that this is an elementary ring. This is the elementary ring that is based on the surface of the frictional lining. Okay, so this is the elementary ring. Okay, so the area of the elementary ring, you can find the area of the elementary ring by taking, okay, its circumferential length. Its circumferential length should be pi d, okay, or 2 pi r. It can be pi d or 2 pi r, the circumferential length. It's just like you have a rectangular strip like that. That means if you break this and you stretch it, it forms a rectangular strip like that. You look at the pointer that I have, a rectangular strip like that. So the length of this strip here would be 2 pi r. So if you multiply by the thickness of this, it will give you this formula here, this equation here. So that gives you the area of the elementary ring. So as we know that force, this is a normal force. So normal force, or this is pressure. And we know that pressure is defined as force over area. The pressure is the pressure exerted by the pressure plate or the spring onto this surface here. Okay, so that is also being perpendicular or 90 degrees to the element here. Okay, so you have this force here. Just look at my pointer. Okay, so this force here will give you pressure. And this pressure is equals to actually the force, the normal force, divided by area. Or in other words, you can also rewrite it as in this form. So the normal force, the small changes, the delta here refers to the small changes based on the elementary ring or the elementary strip, pressure times area. And we know that pressure is P, okay, and then the area that we have developed just now is 2 pi r dr. Dr is actually the thickness of the strip. So you take the circumferential length, multiply by the thickness, this thickness here, you will get the area. Okay, so based on this, then we have to see. Now later on, the pressure here, okay, it depends on whether now we consider uniform pressure theory or uniform wear theory. So if we consider uniform pressure theory, this pressure here will be constant. If we consider uniform wear theory, this pressure here will vary inversely proportional to the radius of the frictional lining. Sorry. Okay, so these are actually the proving formula. So you can just go through it because I have done it for you. So you can just go through it because I need to show you also, okay, how the uniform pressure theory arrives to this formula here. Because earlier we have our torque is equal to this only. This is a general formula for torque. But then if let's say for example is uniform pressure theory or uniform wear theory, then this formula will change to something like that. This is based on uniform pressure theory. Okay, so this is the torque transmitted. So 2 over 3, actually 2 over 3 multiplied by R1 cube minus R2 cube over R1 square minus R2 square. This multiplied by 2 over 3. This, again I repeat, multiplied by 2 over 3 actually can be taken as the mean radius. So as you compare to the previous slide, this one is mu W R and N is the number of pair of contact surface. R here is the mean radius and mu is the coefficient of friction, W is the axial force. So from this you can see mu W is here, okay, N is here. So then you can say this 2 over 3 and this can actually be equals to the mean radius of any single disc clutch with uniform pressure theory. With uniform pressure theory only. Okay, so this is the pressure. We know that pressure equals to force over area. So the area basically when you look at this, the area of this surface here is, okay, pi r1 square minus r2 square. Okay, now take a note here. The note, please read the note here. When the friction surface is new, that means when the clutch is new, there is a uniform pressure distribution over the entire contact surface. So because it is uniform thickness, when the disc is new, that means the thickness of the thickness here, this thickness here, can you say, this thickness here is uniform. So we assume that the pressure distributed here would be the same, uniform throughout. That is what it meant by this. It's a uniform pressure distribution over the entire contact surface if the frictional surface is new. Now this pressure will wear most rapidly, or the disc here, the frictional lining here, actually will wear rapidly, okay, when it is coming into contact with the pressure plate or the flywheel, because it will be subjected to constant rubbing. It depends on how frequent you engage the clutch. So the more you use clutch, the faster this plate here will wear off. So when it wears off, you can see that this thickness here will no longer be uniform. So you can see some of the spaces here will be wear off. It will wear off. So therefore the pressure distribution, okay, on the surface which is initially uniform now no longer is uniform. Okay, this pressure will wear most rapidly where the sliding velocity is maximum, and this will reduce the pressure between the friction surface. This wearing in process continues until the product of PV equals to constant. This P is pressure, this V is what? The volume. Okay, it's constant over the entire surface. After this wear, okay, after this the wear will be uniform. Okay, so initially it's uniform pressure theory. After you have used it for some time, when the things start to wear off and the surface no longer, okay, of uniform thickness, what happens is the pressure distribution here over this surface here will no longer be uniform, and hence you must use uniform wear theory after that. Okay, pressure distribution will be uniform over the entire surface for this case. Now then when you refer to uniform wear theory, okay, since the intensity of pressure varies inversely with distance between P times R equals to C, then you can write P equals to C over R. What is this P? P is the pressure, R is the radius, and is equals to C. So from this, as you can see, okay, the pressure varies inversely proportional to the radius. So means that, okay, when the radius is minimum, the pressure is maximum. When the radius is maximum, the pressure is minimum. So it's no longer uniform pressure theory here. It's uniform wear theory. So you can go through all this. This is a proving formula for uniform wear theory until you arrive to this formula here. That is for the uniform wear theory. This is for the uniform wear theory. And from this you can see R1 plus R2 over 2 is the mean radius. But for uniform pressure theory, the mean radius should be R1 cubed minus R2 cubed over R1 square minus R2 square times 2 over 3. This is uniform where the earlier one was uniform pressure. So note that this statement here that I've given, okay, because pressure and radius here, they are opposite when you take based on uniform wear, when you take uniform wear. So when you have P max, then we have R min, you should refer to R min. Or when you refer to P min, then you should refer to R max. But both cases is actually equals to a constant C. Okay? Excuse. Okay, that's all for this. We'll continue the next slide later. Okay. Thank you.